Okay, so welcome back to this video in which we are discussing transporters. Okay, so at the moment we're just discussing diffusion, and there are two major things that we have seen which can drive diffusion. We have chemical gradients, which we can understand in terms of thinking of chemical potential, okay, and then we have electrical gradients, which we can understand in terms of thinking about electrical potential. Okay, so the next step then is to merge these two together into the concept of electrochemical potential. Okay, and this basically is a way of merging the concept of chemical potential, which drives the movement of solute molecules, and also the concept of electrical potential gradients, which also drives the movement of solute molecules. Okay, so electrochemical potential then. And again, it is just a mathematical model to help us understand reality. And it will be, again, specific for a solute. Okay, so for a certain solute, basically. So you need to pick your solute, and then we can work out the electrochemical potentials everywhere in three-dimensional space for that solute. Okay, so the idea is that you ascribe to every point in three-dimensional space a electrochemical potential. So a real number is ascribed to every point in three-dimensional space, and then the idea is that we can say which direction the solute is going to move based on the electrochemical potential gradient. Okay, so let me give you an example of this. So let's go back to our original example, where we had a much higher concentration of solute in compartment 1 compared to compartment 2. Okay, so we have compartment 1 over here, and then we have compartment 2 over here. Okay, and we had a much higher concentration of solute across the cell membrane here. And then we had low concentration of solute in compartment 2. Okay, so quite clearly we have a chemical potential gradient favouring the movement of solute into compartment 2. But let's now say that this solute is charged. Okay, so let's say that again, these solute molecules are sodium cations. Okay, and now let's mess around with the electrical gradient across the cell membrane. So let's say that the electrical potential of compartment 1 is much lower than the electrical potential of compartment 2. Okay, so to keep it familiar, let's say that the electrical potential difference from compartment 1 to compartment 2 is again plus 60 millivolts. Okay, so that means that the electrical potential is 60 millivolts higher in compartment 2 compared to compartment 1. Okay, sodium ions are positively charged. They want to remain where the electrical potential is lower, which is compartment 1. So now we've got a more difficult scenario to think about. We've got the chemical potential gradient favouring the movement of sodium ions from compartment 1 to compartment 2, but we've got the electrical gradient which says move from compartment 2 to compartment 1. So we now need to be able to merge these two together. Okay, so the chemical potential, which we might denote as C1, the chemical potential of compartment 1 is much higher than the chemical potential of compartment 2. So C1 is greater than C2. Whereas on the other hand, the electrical potential of compartment 1 is lower than the electrical potential of compartment 2. So what we now need, we can't use these anymore to decide which way the solute is going to move, basically. We need to weigh up which one is stronger, so we need a way of combining them together. Now, we're not going to actually look at the formula by which you combine these together, but there is a way of deciding which one will win, basically. How strong chemical potential gradients are compared to the electrical gradients. Okay, and then you can then work out which direction it will move in. But there is this concept of electrochemical potential, okay, which we'll just denote as EC, and we can work out the electrochemical potential of compartment 1. Okay, and again it will be exactly the same everywhere because the chemical potential was assumed to be the same everywhere and the electrical potential was assumed to be the same everywhere. We assume that the formula for working out electrochemical potential from chemical and electrical potential is going to be the same everywhere, so you'll get the same electrochemical potential value for everywhere in your compartment. Similarly, you can work out an electrochemical potential for compartment 2, and basically this combines again the electrical potential and the chemical potential. And now what you can say is that the solute will move from the compartment which has the higher electrochemical potential to the compartment which has the lower electrochemical potential. So when you didn't have to think about the electrical potential gradient, you could just say that solute would move from the compartment of higher chemical potential to the compartment of lower chemical potential. Okay, when we didn't really have to worry about the chemical potential difference, i.e. we had the same concentrations on both sides, the same chemical potentials, we could just say that the solute would move from the area of higher electrical potential to the area of lower electrical potential. Of course, that assumes that we're working with positively charged ions. It will completely reverse if you use negatively charged ions, but that's a different story. Okay, and to simplify it, we'll say we're using positively charged ions. Okay, we have now combined these two into some clever combination, okay, called the electrochemical potential, and we can now say that the ions will move from the compartment of higher electrochemical potential. So let's say that the concentration gradient was actually stronger than the electrical gradient, okay? So we're going to get a net movement from 1 to 2. That would mean that the electrochemical potential of compartment 1 was greater than the electrochemical potential of compartment 2. Okay, so electrochemical potential is just this number that allows us to understand which direction solute will move when we've got both an electrical gradient and a chemical gradient which might not necessarily agree with one another. Okay, right, so you'll always move from the area of higher electrochemical potential to the area of a lower electrochemical potential. Okay, so that's what electrochemical potential means, basically. Okay, right, so let's now talk about actually getting across the cell membrane, because what this is all about, this is telling you overall which direction are you going to get solute molecules moving. Okay, so if you've got an electrochemical gradient for these solute molecules across the cell membrane, then we can work out from that which direction they'll move. Okay, so let's say we do indeed have an electrochemical gradient for oxygen across the cell membrane. Okay, so let's say that the electrochemical potential for oxygen is higher extracellularly than it is intracellularly. So we've got this favouring of the movement of oxygen inwards. However, it's not as simple as that, because we also have to consider how fast will this actually happen. How easy is it for oxygen to actually get through the cell membrane? Okay, so when we consider movement across the cell membrane, we don't just have to consider, okay, in the ideal permeable membrane case, which direction would you get movement in? We also have to consider how fast will this movement actually occur, basically. And how fast it will occur depends on how easily it can actually cross the membrane. So if you like, what we've just been discussing is the thermodynamics. We've been discussing, okay, if you left it for an infinite amount of time, what would eventually happen, basically. Okay, whereas we need now to discuss the kinetics, which is how fast will it actually occur. Okay, and that's going to depend on how permeable the membrane is to our solute. Okay, so if the membrane is permeable, all of what we've discussed applies, and the net movement of solute will be down the electrochemical potential. Okay, whereas if the membrane isn't permeable, then it doesn't really matter that if it was permeable, this is the direction it would move in, because it can't actually move if the membrane isn't permeable. So we now need to discuss about membrane permeability, and this is where transporters become so important. So, basically non-polar molecules, okay, which are hydrophobic molecules. So, for example, oxygen is an example of a non-polar molecule. What it really means is that there's no unequal distribution of charge. So you don't have a positively charged portion and a negatively charged portion. The molecule is completely homogeneous with regards to the presence of charged particles. Okay? Now, the reason that you don't have an unequal distribution of charge is because you've got two identical atoms bound to each other in this oxygen molecule. Okay, so this oxygen atom will have the same electronegativity as this oxygen atom. So let me discuss what electronegativity means in a little bit more detail. So, if we've got our oxygen atom here, drawn now bigger, we know that in each of these two covalent bonds you have one electron from each of the two oxygens. So in this covalent bond, this oxygen puts in an electron and this oxygen puts in an electron. In this covalent bond, this oxygen puts in an electron and this oxygen also puts in an electron. Okay, so the electrons are sitting in between the two oxygen atoms. Okay, now the nuclei of the oxygen atoms contain positively charged protons. They also contain neutrons, but those are neutral, so we don't need to think about those. The point is that the nucleus of the oxygen atoms are this center of positive charge. Now, those nuclei are exerting pulls on the negatively charged electrons. Now, the electronegativity of an atom means how strongly does the nucleus of that atom pull on electrons which are in a covalent bond like this. Okay, so if you have a very high electronegativity, it means that the nucleus is going to pull very strongly on the electrons within a covalent bond like so. And if you have an atom which has a very high electronegativity bound to an atom which has a lower electronegativity, then of course the atom which has the higher electronegativity will pull the electrons towards it and away from the atom which has the lower electronegativity. So the electrons will end up tilted to one side, and that will give this side where the electrons are present a partial negative charge, and the side where they've been lost from a partial positive charge. Now, oxygen does have an extremely good electronegativity. Okay, the ability of the oxygen atom nucleus to pull on electrons is very high. But of course we bound it to another oxygen atom, so it doesn't get to have any fun with this, because both of them will be pulling on these electrons extremely hard, and no one is going to win. It's a tug of war where nothing is happening, basically. So the electrons will remain in the middle, and therefore you won't get a polar bond being formed here. Okay, so that's the main reason that these oxygen molecules are so non-polar. Okay, so another word for non-polar would just be to say neutral. Okay, right. So, if you are very, very neutral, you can easily get across the lipid bilayer of cells. Okay, so let me show you the lipid bilayer. So, the phospholipid bilayer is made up of this bilayer of phospholipids. So you have one layer of phospholipids like so. And phospholipids are usually drawn with this cartoon structure. Okay, so you have a polar head like so. And there are many different types of phospholipid, and they all share this same sort of structure. They have a polar head which will contain a phosphate group. Okay, so this is a polar head which contains a phosphate group, and the phosphate group will be negatively charged. Now they also have they often also have other structures attached to the phosphate group which can vary vastly, and these can also be charged. The point is that the polar head most definitely has the phosphate group in. Even to be considered a phospholipid, you have to have a phosphate group in, and phosphate groups are always charged, so they're going to be within the polar head of the phospholipid. Okay, right. Then you have these long hydrophobic tails, and at least one of these will be made up from a long-chain carboxylic acid. That's the criteria that you have to obey to be considered a phospholipid. You have to have a phosphate group within your structure. Okay, and you also have to have a long chain carboxylic acid. Okay, so you have to have a fatty acid, as they're called, an Fa, which is just a really long hydrophobic carboxylic acid molecule. Okay, right. So if you obey those two criteria, you are considered a phospholipid. Now, in reality, the phospholipids that we have within the phospholipid bilayer generally have two long hydrophobic tails. This second one might not necessarily be a long chain carboxylic acid. In the phosphoglycerolipids, and don't worry if you don't know what that means, you do have two long chain carboxylic acids. In the sphingomyelins, that is not a long chain carboxylic acid. Instead, it's the tail of the sphingosine molecule. But overall, the message is that you overall have a polar head which has a charge, and then you have these long chain hydrophobic tails, basically. And what's going to happen is the phospholipid bilayer is built like so. So these are many of these phospholipids. And basically, what happens is the polar heads face out either to the extracellular fluid on this side, and let's say this is the extracellular fluid, ECF for short, or into the cytoplasm. And those will interact with the water molecules, okay, because water is a very polar structure and does not interact well with non-polar molecules. Okay. Meanwhile, the hydrophobic tails will come together at the center here, and they'll merge, and you'll have this hydrophobic core of the phospholipid bilayer. Okay, so to get through the cell membrane, which incidentally is usually around 3 nanometers thick, you are going to have to get through this extremely hydrophobic region here, and that means that you're going to need to interact nicely with other hydrophobic molecules. It means that, well, really what you need to have is not be interacting with water. You see, the problem is for polar molecules getting through the phospholipid bilayer is that polar molecules will be surrounded by water molecules. They'll interact very nicely with water molecules, and then when they get to the phospholipid bilayer to go through it, they're going to have to break off all of the water molecules. Okay, so let's say we've got a sodium ion here, which is positively charged. Basically, what you'll end up with is loads of water molecules, and I'll just draw these as little triangles, associated round the sodium ion, and these are known as its hydration shell. Okay? And in order to move through the phospholipid bilayer, it's going to have to break all of these water molecules off, throw them all away, and to do that it's going to require a huge amount of energy to break all those bonds. Then it's going to go through the phospholipid bilayer. It's not going to form particularly strong interactions with the hydrophobic molecules, because hydrophobic molecules don't form particularly strong interactions with one another. So it's not going to get any energy being given out by that. And then it will go back onto the other side, and of course then it will reassociate with its water molecules, and that will release a load of energy. The problem is, this portion in between, you have got to go from being in a low energy state to being in a very high energy state. So basically, if we draw a little energy diagram like this, basically you'll start off at this low energy state where you've got all these water molecules nicely bound to you, and then to go through the membrane you're going to have to go to this high energy state where you've had to detach off all of these water molecules, okay, and that's going to require a lot of energy. And then when you go back onto the other side, you're then going to go down again because you're going to reassociate with your water molecules on this other side. Okay, the problem is this step here, going up here. This requires a large activation energy. Delta G with this funny symbol here means activation energy. Now, where are you going to get that energy from? Well, that's the problem for polar molecules trying to cross the lipid bilayer on their own. Of course, some will just happen to get it. You know, some will spontaneously just happen to get a burst of energy and will be able to do this, but others will not. Okay, so the number that will actually manage to do this will be really negligible, and the rate at which it will actually happen is negligible, and you'll have to wait an extremely long time for the molecules to actually move across, even if there's an electrochemical potential difference across the cell membrane. Okay, so this is the kinetics considerations, which are, is this actually going to happen within a reasonable amount of time? Okay, yes, there is an electrochemical potential difference across the cell membrane, which should mean we should move the solute across the membrane. But if the kinetics are awful, it's not going to happen in any sort of physiological time frame. So this is the case for the most polar molecules, that they cannot cross the cell membrane without help. And this is the motivation for channels and transporters. Okay, but we'll discuss that in the next video.